So in the last video, we calculated delta G by calculating delta H and delta S and bringing them together, and we used heats of formation and entropies of formation. And it was actually kind of a long calculation. So we can also do it in a shortcut method. We can use delta G of formation, and it turns out delta G of formation refers to the reaction where you take elements and you combine them to make them into 1 mole of the substance under standard state conditions. So remember, we are looking at atmospheres, 1 atmosphere for gases. We're looking at 1 mole per liter for solutes. So I should write this down here. And we're looking at pure solids and liquids, and the elements are in their most stable form, so carbon's in the form of graphite, and so on, yada, yada, yada. So we can look these up, and we can tabulate these, and we can write these down. So I'll go ahead and show you a table. So here's a few different substances here. Notice elements, right? It doesn't cost any free energy to form them from their elements. If you take elements and turn them into elements, that's kind of a null reaction. Notice graphite is the most stable form, though. Diamond is a little less stable. So to turn graphite into diamond, it's a non-spontaneous process here on the surface of the Earth. So your pencils are safe forever. However, your diamonds are not safe. So diamonds can actually spontaneously form graphite. They take a million years or so, so you're probably okay. But anyway, these are delta G's of formation. Notice that all of these are tabulated at 298 Kelvin. And the reason for that is that we just have to pick a temperature. And room temperature is very common, and that's actually one problem with this technique. So we can calculate delta G of a reaction by doing the same thing. Essentially, we're just adding up the Gibbs free energy of formation of products and doing the same thing for reactants with all the same kind of symbols as we had before. But these are all at the temperature that our tables are produced at, which are almost 298 Kelvin, almost always. And contrast this with the other technique, right, where we said, well, let's take delta G and calculate it by delta H minus, T delta S. And notice here that the temperature itself could vary. So this is one upside to the technique. It is very, very fast. Fewer calculations. The downside is we're stuck at this temperature. So let's go ahead and use this table to perform a calculation. So let's make some diamond. Let's make some diamond from some methane. So let's go ahead and take some methane gas and imagine a reaction. This is really cool, actually. So we can actually imagine reactions that may not actually occur or not. But nevertheless, we can do a calculation. So is this reaction possible? Now, the only thing is this table over here is at 25 degrees C, so to use it, we really have to be at 25. We got to look up the standard Gibbs energy of formation of all of these. Elements are 0, right? Doesn't cost any energy or enthalpy or free energy to make an element from an element. Diamond is positive 2.9, and methane is negative 50.5 kilojoules per mole. So we do the calculation. So delta G of reaction at 25 degrees C, I guess we should write that in, under standard conditions, is, let me see, 1 mole times by the diamond plus 2 moles times by the hydrogen value minus 1 mole times by the methane. I'm just getting naughty here, writing the elements instead of the proper symbols, so I should really write this as 1 mole times by delta G formation of carbon in the form of diamond, right? That's the allotrope, plus 2 moles times by, I'm sorry, I'm just too lazy for this. So, sorry. So the diamond then is 2.9, and we multiply by moles, and it'll just be kilojoules. The hydrogen, we already saw that was 0. 2 zeros are pretty easy to calculate, I bet. And then we got 1 mole times by methane, so that is minus 50.5 kilojoules. And we can see this is not looking good. So we got a positive number, and although that's negative, that's a double negative there. So we're adding essentially 50.5 to 2.9. And let's see, I think I can do that in my head. That is 53.4 kilojoules. What's the positive mean? Yeah, it's non-spontaneous, so nope, it ain't gonna happen, not without the input of energy. So the methane gas in the gas taps in the lab will not spontaneously break down and form diamond and hydrogen, no matter what we might like to see. We would love to see diamonds coming out the end of the Bunsen burners, but it is not gonna happen. Thermodynamically, not gonna happen, and if thermo says no, we mean no.